Hello and welcome. In this video, we're going to be taking a look at another form of a product between two vectors. Now, in a previous video, we took a look at the scalar product, and it was called that because you take two vectors, and when you multiply them together, you get a scalar. Well, in this video, we're going to be taking a look at the vector product. So it's going to be a different kind of product altogether. We're going to take two vectors, multiply them, and get a vector. Now, it's a little bit trickier to try to define the vector product, so why don't we break it down into a few sort of simple points here. Now, the vector product is commonly known as the cross product. And we'll start off with two vectors in R3, our three-dimensional space. Now, the cross product is denoted as A cross B, proper little time symbol there, as opposed to a dot for the dot product. And this gives us a vector. Now, this vector satisfies a few properties. The first one is that the cross product of A cross B is going to be orthogonal to A and to B. Now, that does mean it could potentially be the zero vector. Knowing that it's going to be orthogonal to A and B, then we have to determine the direction. And the direction of A cross B satisfies what we call the right-hand rule. And let me try to give you a little visual description of what that right-hand rule is. Suppose here I have two vectors, A and B, in three-dimensional space, and theta would be the angle between the two of them. There are two potential directions for this cross product in opposite directions. What we do with the right-hand rule is if we were to place our thumb in the direction of the blue vector A here, because it is first in the cross product, and we have our fingers pointing in the direction of B, which is the second operand of this cross product, then we take a look at which way our palm points. Now, of course, it's very important to make sure you use your right hand, and if you are commonly doing math on paper with your right hand holding a pencil, you got to make sure you put that down first. Use your right hand so your palm points in the direction of A cross B. You can even use the right-hand rule to figure out which direction the z-axis needs to point. That's actually a cross product as well. Take your thumb, point in the direction of positive x, your fingers, point them in the direction of positive y, and your palm points in the direction of the positive z-axis. Same idea. This is how we're going to determine which of the two directions a cross product is going to point. Now that you've got the direction, we still need a magnitude because a vector needs to have both of those components. To calculate the magnitude of a cross product, we have a very similar formula to the dot product. The magnitude, or the norm, of A cross B is equal to the norm of A times the norm of B times sine of this angle between A and B. If theta is 0, then this magnitude is actually 0, and we end up with the zero vector. If the angle is closer to 90 degrees, though, then the magnitude increases. Now, fortunately, we don't have to calculate both the direction and magnitude separately. All of this can be done in a single calculation, component-wise. Now, remember, A and B are in R3, so we may want to just have them component-wise as A being A1, A2, A3, and B as being B1, B2, B3. Given those values, then the cross product, A cross B, is a bit of a complicated formula, but can be easily calculated component-wise. A2B3 minus A3B2, A3B1 minus A1B3, A1B2 minus A2B1. Now, with this formula, you can actually see that if A and B are sort of two-dimensional, or let's say A and B are really just vectors that lie on the XY plane with their A3 and B3 components equal to 0, then this cross product, as kind of expected, should either point directly upwards into the positive z direction or directly downward into the negative z direction. You can see that here by letting A3 and B3 equal 0 in that formula. Now, it's actually a lot easier to calculate the cross product using what we call a determinant rather than memorizing this formula. Now, a determinant is something that you learn in a course on matrix algebra. And if you've taken a course like that, then you'll already be familiar with the determinant, and you know it's pretty quick to calculate. Good news is, if you haven't done any matrix algebra in the past, then you don't need to take a full course in it in order to be able to just calculate the determinant that we need for this purpose. It just involves what we call a matrix, which is an array of values. It's arranged into rows and columns, in this case, specifically 3 rows and 3 columns. And then we operate on that matrix using this operation called a determinant, and that produces the result we need. So let me show you step by step how you calculate the determinant for a cross product specifically. We're going to set up a 3 by 3 matrix. In the first row of this 3 by 3 matrix, we have our elementary unit vectors, I hat, j hat, and k hat. In the second row of this matrix, we have the 3 components of A. A is the first operand in the cross product, so it has to be on the second row. And B is the second operand in this cross product, and it needs to go on the third row. Now, to form the cross product of A cross B, we use a determinant, and that's indicated as these 2 vertical bars on either side of that 3 by 3 matrix. Now we're ready to start calculating it. Now, a determinant is a recursive definition. In order to calculate the determinant of a 3 by 3 matrix, we actually need to use determinants of 2 by 2 matrices. Let's start off with this first row and write each entry down. So that'll give us I, and that's going to be one term of our determinant. J is going to be a second term of our determinant, and K is going to be a third term of our determinant. Now, as you go from the first to the second to the third entry in the first row, each term is going to alternate signs. So our first term is going to be positive, our second term is going to be negative, and our third term is going to be back to positive again. Each term consists of a product of one of these elementary unit vectors and a determinant. Since I is in the first row and first column, what we do is we actually get rid of the first row and first column of this 3 by 3 matrix and write the remaining entries down. That would be A2, A3, B2, B3, and calculate the determinant of that 2 by 2 matrix. Since j hat is in the first row and second column, we eliminate the first row, second column, write the entries that are remaining down, A1, A3, B1, B3, and calculate the determinant of that 2 by 2 matrix. And then, since k hat is in the first row, third column, we eliminate the first row, third column, and write the remaining entries down, A1, A2, B1, B2, and calculate the determinant of that 2 by 2 matrix. Now we've taken this 3 by 3 determinant and broken it down into 3 separate 2 by 2 determinants. And then we can kind of repeat the same process again. Let's start off with this first term. We already have I hat. For the determinant of the 2 by 2 matrix, we're going to start off with the entry in the first row and first column, which is going to be A2. We're going to eliminate the first row and first column, and that just gives us B3, which is just a single entry. So that'll be A2 times B3. Now we're going to go to our second term in the determinant. Going to the first row, second entry, that is A3, but we have to remember the alternating sign rule. That gives us a second term that starts off with negative A3. We eliminate the first row, second column of this 2 by 2 matrix, and that gives us simply just B2. And that gives us the determinant of that 2 by 2 matrix. We don't have to continue doing more and more determinants at this point in time, since A2 B3 minus A3 B2 is simply just going to be a number. Now, it's quick to do these 2 by 2 matrices. It is essentially the main diagonal going from top left to bottom right, multiplying entries, and subtracting the reverse diagonal, A3 times B2. Let's try that with the second term here. In our second term, we still have minus j. And then we're going to do the diagonal method here, A1 times B3 minus the reverse diagonal, A3 times B1. And then we get to our third term. We have plus k hat. And then we're going to do the main diagonal, A1 times B2 minus A2 times B1. Now, we're actually done the determinant at this point in time. We started off with 3 by 3 determinant, broken down into 2 by 2 determinants. And when we break 2 by 2 determinants down further, we just get to real numbers and the process is done. It may just be a little bit beneficial to write our A cross B vector in this kind of component form. We have our X component, I hat, Y component, J hat, and Z component, K hat. Just be really cautious about this one negative sign here on the j hat component. And there we go. We've computed a determinant. Keep in mind that determinants can be generalized to higher dimensions. We can take the determinant of a 5 by 5 matrix in a similar way. However, we are only going to be really needing this for 3 by 3 matrices for the purposes of computing the cross product in R3. Now that you see how to calculate the cross product of two vectors in general in 3 dimensions, let's try this with a couple actual values and do an example now. Let's suppose that we have two vectors. The vector A will be -2, 1, 2, and the vector B is 3, 2, 4. Well, in order to get the cross product, it's best to use this determinant form. And in the first row of our matrix, we have our elementary unit vectors I, j, and k. In the second row, we have the vector A, and in the third row, we have the vector B. Now, just remember that if we were to look for B cross A, then we'd have to switch these second and third rows. Now, remember with the determinant that we have alternating signs across the top row. We're going to have 3 terms. The first term will give us our I hat, our x component. Our second term is going to be negated, and that's going to be the j hat or y component. And the third component is back to being positive, and that's k hat or the z component. Starting off with I hat, we're going to just eliminate this first row and first column, and then we'll use the diagonal method to calculate this 2 by 2 determinant. The main diagonal, 1 times 4, minus the alternate diagonal, 2 times 2. All right, now moving on to the j component, we're going to eliminate this first row again, but this time we're eliminating the second column, and we'll use our main diagonal, -2 times 4, minus 2 times 3. Of course, remember that that's going to end up being negated after we've computed that value. Now to calculate the k component, we're still going to be eliminating that first row, but we're going to be eliminating the third column now, and we'll look at the determinant, -2 times 2 minus 1 times 3. Now it's just a matter of calculating the value of each of those 3 terms. Starting off with I hat, that component is 0. The j hat component, once we take into account that negation, gives us positive 14, and our k component, or our z component, is going to be -7. This could always just be written in triangular brackets as an ordered triple. 0, 14, -7. Perfect. So it's a fairly straightforward computation as long as you kind of remember the alternating signs across the top row and the alternating signs of our forward diagonal and backward diagonal. All right, to help you visualize the cross product, I've just brought up Maple here, and we've got a couple packages, the plots package to help plot in 3 dimensions, and the vector calculus package as well, and we'll see that one again in the future. Now, with those packages included, we can start defining a couple of vectors, A and B, and we could use this command cross product. And of course, that will just compute the vector product of A and B. Now you'll notice if I have cross product AB versus cross product BA, you get the exact same components, simply just negated. However, instead of the cross product command, you can always take a look, and you'll be able to find this if you're looking for the times symbol. A times B will also give us the cross product. I've got that stored here as AB, and I'm using the arrow command, which helps to plot vectors. We've got 3 vectors, A, B, and our cross product, with a couple options to try to make it look a little bit more pretty. Okay, now the first thing you'll notice is they don't all look particularly orthogonal. This cross product is supposed to be orthogonal to those other 2. If we just go back to 1-to-1 scaling or constrained scaling though, you can see, oh, there we go. That long vector, this purple to green vector, is in fact orthogonal to these other 2 short vectors. That would be your A and B, and this is going to be A cross B. Now you can even try to figure out which of those is A and which of those is B using the right hand rule. Your thumb should be pointing in the direction of one vector, and your fingers pointing in the direction of the other, and your palm pointing in the direction of this cross product. Okay, now that you know how to compute the cross product of 2 vectors, it may not be totally clear as to why we would calculate it this way. So let's take a look at a few properties of the cross product so you can get an understanding of sort of what kind of behaviors it follows, and that should hopefully help it to make more sense. But also we can take a look at some applications. Now, for the purposes of defining some properties, let's assume that we have three vectors that are all in R3, A, B, and C. Now, I'll try to be a little less confusing than maybe in my dot product video, and let's say that K is a real number, just to make sure that we can distinguish between C and K this way. First of all, there's some kind of interesting properties that you would expect for multiplication that don't hold true with cross products. Because of the right-hand rule, we don't have a commutative property. In fact, A cross B and B cross A, well, they give us the same magnitude, but the right-hand rule gives us opposite directions, and that's where this negative sign comes in. They are equal in opposite directions. Fortunately, we can say that the cross product follows the distributive properties that you'd expect. If we have a sum of vectors, B and C, and then we want to take the result and have A cross B plus C, then we can distribute the cross product from the left. Of course, you can also distribute the cross product from the right. The commutative property means we have to be very careful about which way we are distributing. This would mean that if we want to take the sum B plus C and have the result B plus C cross A, then we have to distribute from the right, and we cannot say that these two are equal to each other. In fact, once again, by that first property, they're going to be equal magnitude, but in opposite direction. Now, if you remember when we looked at the dot product, this associativity idea, A dot B dot C, doesn't make any sense because the dot product of two vectors gives us a scalar, and then it would simply become scalar multiplication of a scalar and a vector, and we couldn't do the dot product. But the vector product, or the cross product, A cross B, gives us a vector, so we should be able to then look at the cross product of a cross product. That would make sense. However, some of the behavior is not quite the same with cross products as you would expect with the multiplication of real numbers. In general, A cross open parenthesis, B cross C close parenthesis, not the same thing as A cross B in parentheses first, cross C. You may be able to find a case where they are in fact equal, but in general, these are not going to provide us the same result. Something kind of similar to associativity, though, that does kind of obey what we would typically expect is if we have a combination of scalar multiplication and the cross product. A scalar multiple of A, so that would just be Ka. If we were to take the cross product of that and B, then essentially that scalar multiple K, we can do that operation whenever. We can take the cross product of A and B and then scalar multiplication, or we can do a scalar multiple of B and then cross product A and K times B. Okay, those are some common properties, but there's a couple of unique ones here as well. For instance, try this one out yourself here. A cross A is actually going to result in the zero vector. Keep in mind that this is the zero vector and not just a scalar zero. Now, another property is if we want to combine the cross product and dot product, there are some very predictable results here. For instance, the cross product of A and B is going to give us a vector that's orthogonal to A. And then if we take the dot product of that and A, that will equal 0 because they are orthogonal. That's the definition here. And similarly, if we were to take the cross product of A and B and dot product that with B, we'd equal 0. And if we do similar combinations of dot products, cross products that result in orthogonal vectors, of course, they're also going to equal 0. All right, now that you've taken a look at these properties, you can see it kind of does obey some of what we expect with multiplication, and sometimes it doesn't obey what we expect with multiplication. It doesn't necessarily help enlighten you exactly yet as to why the cross product or vector product is defined this way yet. Well, we'll take a look at some applications in future videos, and I think you'll understand where it's going to be useful for calculus properties, but for right now, let's see if we can take a look at a couple geometric uses of the cross product. One of the applications of the cross product that we could use right away is actually for calculating area or for calculating volume. Let's start off with a very basic shape here that we can form using two vectors A and B. And let's say that theta is the angle between the two of them. Essentially, with the sum of A and B, we can produce another point out here, and we have a four-sided object with A plus B or B plus A. Now that we've got this parallelogram, let's see if we can figure out how the cross product actually gives us the area. If If you recall, the norm of A cross B is equal to the norm of A times the norm of B times sine of theta. Well, let me just rearrange this for a moment. B times A sine theta. Thinking in terms of right-angled triangles, A sine theta is going to be the length of this perpendicular side here, where we formed a right-angled triangle using theta and using A as the hypotenuse. Well, that essentially becomes the height of this parallelogram, where the norm of B is the base of this parallelogram. And that's exactly how we calculate the area of the parallelogram. We take the length of the base and multiply by the height, just like a rectangle. And hopefully this gives you a brand new way to sort of visualize the magnitude of the cross product. Whenever A and B are both pointing in the same direction, then the area of this parallelogram is 0, and that means that the cross product is the 0 vector. We get the largest area when A and B are perpendicular, and then this becomes a rectangle. Sine of theta, when theta is equal to pi over 2 or 90, is just equal to 1, and then it simply becomes length times width. It's the area of a rectangle. Now remember that A and B, these are both vectors in 3 dimensions. So this is a 3-dimensional parallelogram. It's not just simply relegated to existing on the xy plane. It can be floating anywhere in R3. Now, in order to turn this into a fully 3-dimensional problem, we could add another vector to this mix. Let's suppose we also wanted to add in another vector c. Well, let's write A, B, and C all here together, maybe from like a first octant view, and you can imagine that by taking combinations of vector addition of A, B, and C, we can come up with 6 vertices that form a parallelepiped. This is a 3-dimensional shape. It's not necessarily a cube, although it kind of looks like one here. It's all going to have parallelograms for all 6 sides. How do we calculate the volume of a parallelepiped? Well, it's kind of similar to how we calculate the volume of a rectangular prism. We would take the area of the base and multiply by the height. So same idea here. We start off with the area of the base, which we already know is the magnitude or the norm of A cross B. But what about the height? Now the height is going to be needing to be measured perpendicular or orthogonal to the base formed by A and B. So imagine that we have a ruler here and we are looking for a vector that is orthogonal to the base. Well, that would mean it's orthogonal to both A and to B. Good news is we already know how to do that. We'll take the cross product of A and B. Then we just need to find out what the height is in that particular direction. And we can do that with the scalar projection of C onto A cross B. Now it's important to know that the angle between A cross B and C may be an acute angle or maybe an obtuse angle. They could be nearly pointing in opposite directions. That would produce a negative height, and that's not what we want. So what we're going to do is we'll take the absolute value of the scalar projection as the height of the parallelepiped. Okay, well, how do we calculate the scalar projection of C onto A cross B? If we go back to the video on the dot product, well, that is the dot product of the vector A cross B and the vector C divided by the norm of A cross B. The norm of A cross B is always positive, so we just simply need to make sure that we take the absolute value of this dot product. From there, you can see that the norm of A cross B cancels with the norm of A cross B, and this gives us a really quick formula for calculating the volume. A cross B dot C. It's a combination of the vector and scalar products, and we specifically call this the scalar triple product. Just for the purposes of volume, though, we take the scalar triple product and use its absolute value. And let's see how you can use this in practice to find the volume of a parallelepiped. Well, here's a parallelepiped with 4 of the vertices given. We have P, Q, R, and S. What we're missing, though, is the actual vectors that form the parallelepiped. So let's start off by defining a vector from P to Q. All right, well, that vector, maybe we'll label that as A. And we'll do the same thing with a vector from P to R. We'll call that B. And a vector from P to S, we'll call that C. Let's calculate A component-wise by using Q minus P. That would be -4 minus 1, 4 minus 3, and 6 minus 5. And we'll repeat that with B and with C. Now the scalar triple product, we're going to need to take the cross product of 2 of these vectors and dot product with the third. why don't we go ahead with the cross product of A cross B and then take the scalar product of the result with C. Don't forget, for volume, we take that scalar product and we make sure that it is positive for volume. Let's start off with the cross product. We have our elementary unit vectors, I, J, and K, followed by A in the second row and B in the third row. And then we'll take the dot product of that determinant with 0, 2, 4. Now, at this point in time, that'll give you a little bit of a shortcut, because when we calculate the vector product, then we get a vector. And the thing is we're going to be using the scalar product in a moment anyway, so all we really need are the components that correspond to I, J, and K, and we're going to multiply those values by 0, 2, and 4. So what we can really do here is actually just replace the entries in the first row, I, J, and K, with the entries of C, 0, 2, and 4, and we get the result by just doing the determinant all in one step. Again, we're going to have to make sure that this is going to be a positive value. It's going to be a little bit weird. We're going to have these giant absolute value signs around the whole thing, but it'll be a little easier in a moment. What we're going to do is this clever little shortcut, and we'll replace I with 0, J with 2, and K with 4. Again, we'll have to take the absolute value here in a moment, though it's going to be a bit strange to see determinant lines with absolute value lines outside of it. Now we're ready to calculate the determinant. We're going to take our first entry in the first row, which is going to be a 0, and then look at the determinant of 1, 1, 4, 3. Of course, all of that is going to be multiplied by 0 anyways. Then we're going to get to the second entry in that first row, and don't forget to switch the sign. That determinant gives us negative 5 times 3 minus 1 times 4. Then we'll move on to the third entry in that first row and switch back to positive. Negative 5 times 4 minus 1 times 4. Now the result of adding all those terms together could be negative. We'll have to remember to take the absolute value of the result. And sure enough, the result is negative 118. That just means that it probably would have been better to look at the projection of C onto B cross A rather than A cross B. The good news is it's simply just a difference in sign. We would say that the volume is actually 118 since volume should be positive. Now to help you visualize this parallelepiped, I have defined the vectors A, B, and C with those points P, Q, R, and S. We can go ahead and compute those easily here in Maple simply by subtracting the positions of each of those vertices. And I have this scalar triple product, and I've used B cross A dot C so that I get a positive value. Now, O is just this point P, 1, 3, 5. I'm just using that as kind of the corner of the parallelepiped. I'm using a whole bunch of arrow commands so that I can get all of the various different edges of the parallelepiped. So all of these little plotting tools all put together into one big display. And here you go. You can see that point P with our vectors A, B, and C. And then through some vector addition, I've just basically completed that parallelepiped. That's what it looks like in 3 dimensions, and that will have a volume of 118. All right, well, that's a fairly simple application. You can kind of see how our cross product works with a geometric problem like that. But there's many other applications of the cross product. Another application that you might be familiar with from physics or engineering would be torque. Now, the idea here with torque is that we're going to have some kind of object. It's going to have a pivot point, and we'll have some kind of force applied that's not at the pivot itself. Here you can imagine that with this force being applied, there's sort of a tendency for this object to rotate around that pivot. Torque is going to help us to understand sort of the rotational acceleration of this. Torque, however, is defined as a cross product. This is a vector. Force has both a magnitude and a direction, and we're going to be looking at where that force is applied. We're going to have a second vector that is a position of that force away from the pivot. And you can imagine that depending on the angle between this position vector R and the force vector F, we could have either a clockwise rotation or a counterclockwise rotation, or perhaps no rotation at all if the two vectors are parallel. Torque is defined as a vector, now here, where we take the cross product of r and f, our displacement and force. If we're just looking for the magnitude of torque, then that becomes the magnitude of the displacement vector, or simply just distance, times the magnitude of the force times sine of theta. Now, theta is going to be the angle between r and f in standard position. So we could just see that here as being, if we were to place the initial points of r and f at the same point, this green angle theta would be the angle between the two. Now, what might seem a little bit strange is the direction of torque. As you can imagine, you typically think about torque as being rotational, but this torque vector actually points out of the page if you take a look at the right-hand rule, r cross f. And that is going to seem pretty strange at first glance. But there's another right-hand rule that tells you which way something is going to be rotating if you're given that orthogonal vector. This other right-hand rule is where you put your thumb in the direction of torque, so that'd be pointing out of the page, and then you'd be able to curl your fingers so that you can see which way things are rotating. So put your thumb out of this video towards yourself, and you'll see that, well, the way your fingers naturally curl using your right hand does indicate that this is rotating in a counterclockwise direction, which we kind of treat that as sort of the positive direction coming out of the page that way. Well, there you go. That kind of gives you a couple applications of the cross product. Kind of scratching the surface of what we could potentially use it for. I think torque is kind of a good way to think about where this cross product may be commonly used. You can kind of see it gives us a direction, gives us an idea about which way things may be rotating, but also that magnitude using sine theta makes a lot of sense because we would like to have that force vector and displacement vector more perpendicular to get more rotational acceleration that way. So you can kind of get a good idea about maybe why this particular form of a product is defined the way it is. But stay tuned, because we'll be seeing it again when we're taking a look at multivariable calculus soon enough. So thanks for watching, and I'll see you in the next video.